All right, so this is the introduction video for hypothesis tests. We're going to talk about basically the big main ideas of hypothesis testing. As you can tell from the notes here, this is a lot of material. If at any point in time you need to stop and kind of take some notes, I am going to breeze through the main ideas pretty quickly just so that we can get to the examples in a timely manner. So the biggest thing you need to do first is figure out if you are doing a means test or a proportions test, and then also kind of figuring out what your claim needs to be. So are we looking at means? Are we looking at proportions? And then I actually prefer to write my alternative hypothesis first. That's what you're trying to then prove with your data. Okay, and then the null hypothesis is going to be just the opposite of that. And we'll see some examples at the end of the video once we get through this stuff. Now notice the null and alternative are contradictory. There's no overlap between them. And you have to make sure that you make a decision based on the data on which one of those you think is true. Either we're going to say reject HO if you do think that there is enough information to prove your claim, or we say do not reject HO. And those are our two decisions we are going to make. As far as the signs for your null hypothesis and alternative hypothesis, again, I choose to write my claim first. And so there are a couple different signs that we can use here. Some books do always just say your HO is equal to whatever you like, the standard thing, and you just write these here. Particularly our book at our school does use this notation for HO. So it just kind of depends on your text and what the signage is there for HO or for your null hypothesis. Now we have 4 different possible outcomes in our decision making. If we decide to not reject HO and HO is true, then that is the correct thing. If we decide to reject HO when HO is false, then that is also the correct thing. However, it is possible that HO is actually true and we choose to reject it. We call that a type 1 error. And that's what we assign our significance level to in our test, is the probability of making a type 1 error or rejecting the null hypothesis when that wasn't the right thing to do. There's also a type 2 error, that's the opposite. So if the null hypothesis is not actually true, but we don't have enough evidence to reject it, then that's also an error. Alpha and beta should be as small as possible because their probability of errors, but rarely 0, just because that's just how it's going to work, okay? Another way that I like to think about this is we assume innocence until proven guilty. And so if you reject HO, you're going to send an innocent person to jail. And that would be a type 1 error. If you commit a type 2 error, then you let a guilty person go free. And so that's the difference between those 2 types of errors. Okay, that's helpful. Also depending on your alternative hypothesis, depends on where our rejection region is going to be. If your if your alternative hypothesis is a not equals to, then if we need to evaluate both sides and run what's called a two-tailed test. If your HA is a less than, then we're going to do a left-tailed test. And if your HA is a greater than, we're going to run a right-tailed test. Now, your alpha level depends on what that critical value would be for you to then create that rejection region. You also will be able to calculate a p-value, and if your probability is smaller than alpha, then that is what we're going to say is significant evidence. It is important that we draw a graph and a picture and show what the p-value is in each one of our situations. It's just going to help with context of what's going on. Again, if your p-value is smaller than your alpha, then our decision is going to be to reject HO. There is sufficient or significant evidence, okay, in favor of HA. However, if that's not the case, then we say do not reject HO. There is not enough evidence in favor of HA. And after you make that conclusion, you want to write that type of that statement, okay? All right, so let's just look at some examples and talk through these scenarios here. So let's say that our null hypothesis and alternative hypothesis here, those are given to us. No more than 30% of registered voters in this county voted. But what looks like what I'm trying to prove or what I'm trying to claim is actually more than 30% of registered voters in that county did vote in the primary election. So maybe that's something I'm trying to show or prove here. Well, the way in which we're going to do that is you're going to use your HO for your center of your distribution. And so what you can kind of draw here is that we think 30, and those P's there, they should be 0.3 zeros because they're a proportion, okay? Our like HO, right, is less than or equal to that. But if I have a P hat, a sample proportion that I collect that ends up being having a critical value in this rejection region, then I would have significant evidence in favor of HA. And that's basically what we're going to be trying to find here. Let's say I want to test to see if college students take less than 5 years to graduate on average. Well, that on average means I'm looking at means. I'm going to go out and collect a sample, and I want to know how long it took them to graduate from college. And I'm trying to prove that this is significantly less than 5. So this would be a left-tailed test. So this would be my rejection region. And so I'm trying to figure out if I can find an X bar in that rejection region. If I can, then we would say there is enough evidence to prove it does take less than 5 years. If I can't, then I don't have significant evidence in favor of that alternative hypothesis. Average amount of time boys and girls aged 7 to 11 spend playing sports each day is believed to be the same. However, maybe we might want to prove that they are just different. Notice in this problem stem, it doesn't say one is bigger than the other. It's just like they're believed to be the same. Here's some data, and then here's your hypotheses. So in this case, this is called a two-tailed test because I just want to know if they are actually different from each other or not. So when I go to set up my alternative, notice right here, or my distribution of what's going on, what my testing distribution is going to look like. Notice that I'm actually setting that the difference between them is 0. And since I'm saying not equals to, I actually have a two-tailed distribution. So I have 2 pieces of rejection region on each piece. Based on this sample data, I would have like an X bar G, and I would have an X bar B, and I would subtract those. And then that's what I want to test and see is that difference in those rejection regions. All right, researchers conduct a study of smartphones Cell phone company claims that iPhones are more popular with whites than with African Americans. Results of this study, and it gives all the information, test this at a 0.05 significance level. If you do see that, we're not actually going to run the test. We're just talking about this like big picture. That's your alpha level. Okay, and it will give you that in the problem. And if it doesn't, then that's kind of what we default to. And we want to know, is the proportion of white iPhone owners greater than for African Americans? And so notice how the hypotheses here are set up. Again, on this distribution, I do set that difference in the middle to be 0. I do have some information here for me to find two sample proportions and subtract them from each other. And then I want to do a right-tailed test. So I can reject this if that difference is in the rejection region. All right, this is our last example. A study was conducted to investigate the effectiveness of hypnotism in reducing pain. Results for randomly selected subjects are shown. The lower score is less pain. There is a before and an after value. And the differences follow a normal distribution. That's nice. Again, they give us a significance level. Now, the difference here is before, when we looked at two different means, notice it says on average. Before we looked at two different means, these were two different groups. We had a girl group and a boy group. In this problem, we only have one group, right? We have 1, 2, 3, 4, 5, 6, 7, 8 subjects, one N value with a before and an after. So note how this is set up. It does the population mean for the differences. So in another like row here, you'd have to find the difference. We probably would do, let's see, it wants to lessen the pain. So I bet it's after minus before, because you want less pain after. And so after minus before should result in negatives if your pain is decreasing. And so this would be a left-tailed test where you would want to figure out if your like X bar D is in your rejection region right here.